It's recording. Okay. Hello, everybody. Welcome back. So today we have the fourth and the final lecture by Professor Horatiu Nastase, right? So last time we learned many things. We learned Lipschitz scaling. We learned some QCD-like theories. What else? Okay, I forgot a few other things.
And the PP wave correspondence.
That's correspondence. That's what. Okay, how can I forget that? That's what Horatiu is famous for, right? So yeah, we did the PP wave in Penrose limit and other things, right? So fantastic. So today, I think that covers the first three lectures. Cover all the things in Horatiu's first book on AdS CFT. And today's lecture is about application of string theory to cosmology. He has a book on this alone, right? So I strongly advise you all to go check that out. Okay, so with that said, Horatiu, please go ahead.
Thank you. Let me go. Where is it? Yeah. All right. So thank you for the introduction. And as we said, this is actually the last lecture. And after all, after the previous three lectures, I described the basics and the formalism of AdS CFT and gauge gravity dualities. Today, I will consider an application that is actually more in line with the lecture series, namely holographic cosmology, which intends to apply the ideas of gauge gravity duality to obtain a cosmology in the regime of strong gravity. So something that otherwise would not be possible to obtain, but now we will do this through the gauge gravity duality. So first of all, as I said, this is an example of gauge gravity duality. And it's a non-conformal type. Obviously, cosmology is not conformal. Let's first understand an example, a top-down example of such non-conformal gauge gravity duality. This is an example that was done shortly after the paper of Maldacena by these people, Itzhaki, Maldacena, Zonenschein, Yankelovich. So one considers ND2 branes in a decoupling limit, and that will give a 2 + 1 dimensional superamnios with gauge group SUN. And the metric now is not AdS because this is not conformal. As I said, AdS corresponds to conformal field theory boundary. But we have, on the boundary, we have this three-dimensional flat space. And the decoupling limit, as before, corresponds to taking a low energy limit, meaning alpha prime to 0, and also taking a near horizon limit, which means r going to 0, while keeping the ratio r of alpha prime fixed. The one difference now is that the relation between G Yang-Mills and G string, since we are in 3 and not in 4 dimensions, involves also a dimensional quantity alpha prime. So G squared Yang-Mills is G string over square root alpha prime. Accordingly, G squared Yang-Mills has mass dimension 1. So in the decoupling limit, we look at this function h, and we see that the second term is much bigger than the first, so we drop the 1. And then so then we get a so-called gravity dual. As we said, the general gravitational background is called the gravity dual, that has 3 + 1 dimensions, not AdS4, but rather something like a warped AdS4 in some sense. And then a 6-dimensional sphere. So in this case, duality is holographic as well, in the sense that the gravity part, once we reduce on omega-6, is 3 + 1 dimensional. And then the field theory part is 2 + 1 dimensional. So this is an example of a top-down duality. But as we said last lecture, in particular in AdS CMT, but not only, we will use this also here, one considers also phenomenological type of gauge gravity duality, bottom up. And in particular, the application I'm interested in now is to cosmology. The example that we considered last time to AdS CMT was we considered some gravity theory in AdS space, and we assumed there is holography, and therefore, by the holographic map, we obtain a dual non-perturbative field theory that we actually don't know in general, but we know its desired property through the holographic map. So the phenomenology was going from AdS towards field theory. But now we want to go the opposite way. We want to go from field theory to an unknown gravity theory. So we define a perturbative field theory phenomenologically, and then by the duality map, the holographic map, the perturbative field theory will correspond to a non-perturbative, that is highly quantum gravity. And it will be defined implicitly by the holographic map. So even though we don't know what it is, the holographic map defines it implicitly, giving us some desired phenomenology. So just to fix things, because this is rather unusual with respect to what we usually do, let's understand the cosmology has 3 spatial directions that we'll call perhaps X, Y, and Z, and time t. And then on top of the cosmological background, FLRW, one considers fluctuations for the, let's say, for the spatial metric Hij and for some scalar. So those are functions of these 3 spatial coordinates and time. However, in order to apply AdS CFT, or rather gauge gravity duality, to it, we have to do a double Vic rotation such that instead of XYZ, we have now TXY. So the time is now part of the boundary field theory. And instead of time, we have radius. So that this extra coordinate, now the coordinate away from the field theory, corresponds in cosmology to time. So once we do this, we understand the RG flow in momentum or in energy U in the field theory was mapped, as we said last lecture, to evolution in the radial coordinate r away from the boundary field theory. But now, through the double Vic rotation, this is mapped to time evolution. So, in conclusion, we have RG flow in the field theory mapped to time evolution. More precisely, inverse time evolution, or inverse RG flow to time evolution. Okay, so let's understand a little bit about the picture we want to obtain. So first of all, what's the current model? The current model is inflation, and inflation would correspond to an exponential expansion. So A proportional to e to the h of t, or some high power law with power greater than 1. So A of t proportional to t to the n greater than 1. This is almost a standard model of cosmology because it because, among other things, so the most important things are that it agrees with the data, with the CMBR fluctuations, and solves a set of classic puzzles with usual hot Big Bang cosmology, pre-inflationary one. But now we want to consider, in some sense, an extension of this inflationary paradigm into the strong gravity domain. And being strong gravity, we can deal with it holographically via gauge gravity duality and calculate things in perturbative field theory. And this will be called holographic cosmology. Now, I should emphasize that when people say holographic cosmology, many times they mean different things. So the specific holographic cosmology I'm talking about is this setup here. And moreover, the phenomenological setup defined by McFadden and Skenderis in 2001, which uses specific types of 2+1 dimensional quantum field theories, ones with so-called generalized conformal structure that I will define. So not conformal invariance because it doesn't correspond to AdS, but generalized conformal structure. And we will fix the parameters in this field theory phenomenologically by fitting through to the CMBR data. And when one does that, one obtains a different parametrical fitting rather than the usual fitting of lambdas called dark matter plus inflation. But nevertheless, the fit to the CMBR of this holographic cosmology we'll find is as good as for inflation. So chi squared is a difference of 0.5. So one says when chi squared is less than 1, the fits are indistinguishable. So in one case we have chi squared of 824.0, and the other side 823.4. Now, and the other point is that this will be possible to be improved by lattice calculation at some intermediate coupling. So instead of using just small coupling, perturbative, one can do things on the lattice for field theory. And this is in progress by a lattice group that includes Kostas Skenderis. And so this is with respect to the fit to the CMBR. And then we said another reason why considering inflation, besides the fits to CMBR, are the classic puzzles of cosmology of the pre-Big Bang, the pre-inflationary hot Big Bang cosmology. And we'll find that these puzzles are also solved by holographic cosmology. All right. So what is holographic cosmology? As we said, when one has to Vic rotate the cosmology, and instead of the time direction, so we Vic rotate the time direction to a radial direction. I'll call it Z here. Before, I mean, it's basically 1/r from before. So we write the Vic rotated cosmology as this gravity dual. And then we'll also have some scalar field, as we said in cosmology, we usually have a scalar field, which has some background plus a fluctuation that is modified by the same is multiplied by the same Z. And so this Vic rotation comes with also a Vic rotation of the momenta. Q bar is minus IQ, and of also, which is slightly more bizarre, of the the square of the gravitational coupling. So kappa bar Newton squared is minus kappa Newton squared. And then this cosmology would correspond to some phenomenological gravity dual. Which means a gravity dual in which we write the most general we will write not gravity dual, field theory dual, I should have said. So we write the most general field theory consistent with what we want, and then we fix its parameters. And for the field theory, the Wick rotation corresponds to, well, the same for momenta, but this condition on kappa Newton corresponds to n bar is minus in. And that might sound bizarre since n is the n of SUN. But the point is, remember, I insisted on the fact that when we consider gauge gravity duality, the gauge group disappears. So the only thing that is left is n as a parameter. So that's what we're doing here. We do calculations, and at the end of the calculations, we Wick rotate the parameter n. So this does not need to be thought of as Wick rotating the gauge group. Then we have to think about these fluctuations. That's really what we're interested in. So we know that in inflation we want to fit the quantum fluctuations of the inflaton to CMBR observations, and that's what we will like to do here as well. So one must obtain power spectra for the perturbations, the gauge invariant perturbation, tensor perturbations, including the metric and the scalar. So gauge invariant combinations of Hij and delta phi. These are delta scalar squared and delta tensor squared, the 2-point functions of zeta and of gamma ij. So these are the things that are fit against CMBR observations. But now we have to calculate these things in our holographic cosmology. So how does one do that? Well, this was started by an idea of Maldacena in 2002. So if one considers inflation like Maldacena did, Maldacena only considered inflation, exponential inflation, I should say, a of t proportional to e to the h of t. Then via this Wick rotation, we would have a of z proportional to e to the hz, so exponential scale factor. This would correspond to an approximately de Sitter gravity. And then de Sitter itself was considered by Maldacena to be, in some sense, a type of Wick rotation, not really Wick rotation, but a type of Wick rotation from anti-de Sitter. So going from anti-de Sitter to de Sitter, one is able to do a Wick rotation-like transformation on parameters. And when one does that, Maldacena found the following prescription. So one starts with a Witten prescription in AdS, which was that the partition function in the CFT as a function of some sources phi 0 is the partition function of AdS, where these phi 0 now correspond to boundary sources for the fields. And this partition function in the supergravity limit is just E minus the supergravity action that depends on these fields. When one does this Wick rotation, Maldacena finds a prescription or map where now this CFT in the partition function in the CFT, depending on, well, these phi's, but also now fluctuations of the metric, Hij, is equal to the wave function of the universe, psi, as a function of the same Hij and phi. So what is a wave function of the universe? I mean, if you're following quantum gravity, you probably know, but the wave function of the universe is the path integral up to a surface with a certain, where I define the values that the wave function depends on. So the 3 metric and the phi at some time t. So one does a path integral over everything with these boundary conditions. Okay, so that is the prescription of Maldacena. And then further, this was extended to non-conformal theories by works of Skenderis et al. So in particular to things like the D2 brane example that I gave to you, in which case one finds power laws instead of exponential A of t, one has power law. So in the gauge gravity dual, one finds A proportional to Zfn, which means A proportional to T to the N in cosmology. Moreover, as for the usual AdS CFT, we assume it is valid at any coupling, including the strong or non-perturbative quantum gravity, right? So inflation is weakly coupled. But now we apply this also to the strongly coupled regime. In fact, as I emphasized, this is really a variation of inflation, a strongly coupled form of inflation. So the holographic cosmology that we're describing here is nothing but inflation in the strongly coupled regime. And there we can say something about it through field theory. So the new model then says that the CMBR perturbations that we observe in the sky are perturbations that were created during this strong gravity or non-geometrical cosmological phase. And after that, eventually, we have to reach the geometrical or weak gravity regime. But the things that we see now in the CMBR are perturbations that were generated during this strong gravity regime. Then a certain holographic, that is to say, strong gravity or perturbative, corresponding to perturbative field theory calculation, which is either a direct one based on a formulation, a Hamiltonian formulation found by Ioannis Papadimitriou and Kostas Skenderis, or based on directly on this extension of the Maldacena map, the partition function versus wave function of the universe, extended to this case, gives the following formula. So for the scalar spectrum, we have cubed divided 16 pi squared times the imaginary part of a B defined at this Vic rotating momentum. The tensor perturbation, the same thing, where I have switched with an A instead of the B. And the A and B are just scalar functions appearing in the two-point function of stress energy tensors. The two-point function of stress energy tensor can be decomposed in these two scalar structures multiplied by some tensor structures that involve the momenta, involve delta ij and qi. So, okay, so we found what the scalar and tensor structures in the CMBR, seen in the CMBR, should be as a function of these A's and B's in the two-point function of energy momentum tensors. So how do you calculate that? More precisely, what is the theory in which we calculate that? Well, we will calculate in a Euclidean field theory, Euclidean because, as we said, it's a double Vic rotation. So if we do just one Vic rotation, the X, Y, and Z of cosmology correspond to the coordinates of field theory. And the theory must be super normalizable and have generalized conformal structure. Generalized conformal structure means the following. It means that dimensions in this theory, the only dimensions, are contained in the dependence on Q, and specifically through this effective coupling G squared n over Q. Remember, in 3 dimensions, G squared has dimension 1. So G squared n over Q is dimensionless. So if we write the action will be a phenomenological one. So I write the most general theory that has these two properties of being super renormalizable and having generalized conformal structure. So for the QFT, I write then what? Well, I have to write, as usual, spins up to 1, which means scalars, fermions, and gauge fields. And the generalized conformal structure means the only dimension comes in with a coupling. There's no with a Yang-Mills coupling. There's no other dimension. So I write specifically the G Yang-Mills in here, and then everything else, these mu m L1 L2 and these lambda M1 M4 are dimensionless. So these are couplings for Yukawas and 5-4 interactions. Another way of saying it is that if I now rescale, if I write the action in the form with 1 over G squared Yang-Mills in front and then no other G Yang-Mills in the action, the thing that multiplies it doesn't have any dimensionful parameters, right? So I write it like this, then I have the kinetic terms and these Yukawa and 5-4 terms with dimensionless coefficients. And yet another way of thinking about it that is consistent with this is that if I would imagine this action as being derived from 4 dimensions by dimensional reduction, the 4-dimensional action would be conformal, right? Because if I have a 4-dimensional conformal action, right, the only thing that happens when I dimension reduce, I multiply the coupling 1 over G squared Yang-Mills with an integral over the circle, so with a 2 pi r. And in here things would be 4-dimensional conformal. All right, so this is the field theory that I'm considering. And in this field theory, as we said, the A and B are the coefficients of the tensor structures in the 2-point function of energy momentum tensors. And because of the notion of generalized conformal structure, so because generalized conformal structure is a symmetry or property of the action, these A and B's can only be functions. Well, we have this cubed for dimensional reasons, and then squared again, because we have n squared. Yeah, this is the action is proportional to n squared. But otherwise, the functions that appear in here, ft and f, are scalar functions of this dimensionless effective coupling, G squared Yang-Mills n divided by q. And so then one calculates this 2-point function of energy momentum tensors in field theory at 2 loops. And at 2 loops, one obtains the following form, and higher loops are contained in these terms that were dropped. So one obtains, well, a constant in front, multiplying 1, and then the corrections are of 2 types. There are corrections of G squared effective and of G squared effective log G squared effective. This is standard in quantum field theory. Well, standard in 3-dimensional quantum field theory. And then remember that the scalar and tensor 2-point functions were equal to something proportional to 1 over imaginary parts of A and B. So we take 1 over imaginary parts of these A and B, and it's easy to see then that we obtain for the scalar and tensor power spectra something like a constant divided by 1 plus an effective coupling. So therefore I have something like GQ star divided by Q, where Q is the momentum, log Q divided by some other beta GQ star. And for the tensor, something similar with different G and beta. So I have, in other words, I have something of the type 1 over 1 plus log Q, where the coefficient is also 1 over Q. And so this is a phenomenological parametrization, but all of these phenomenological parameters, G, Q star, beta, GT, beta T, depend on the parameters of the phenomenological action, on G squared Young-Mills, on N, number of scalars, number of fermions, and the couplings lambda and mu. So now let's understand a little bit, since this is the part that confuses most people, I think. Let's insist on the issue that why do we get a spectrum that is almost exactly the spectrum obtained from inflation fluctuations, right, for the CMBR? So in particular, why is the spectrum almost flat? Well, the answer is this generalized conformal structure. The only corrections I'm allowed to have are corrections in this G squared effective, G squared N over Q. And we're doing perturbation theory, so this G squared effective is small. So then the only possible perturbations are G squared effective or G squared effective log G squared effective. There's no other perturbations allowed. There's no other other parameters allowed at the 2 loop. 1 loop is the 0th order. So then we get really this form. This is just this form is really nothing but nothing but generalized conformal structure in perturbation theory. So then, why do we get something that is similar to lambda called matter plus inflation? Well, in lambda called matter plus inflation, the scalar perturbation, for instance, the tensor is the same, is parameterized as follows: is the constant, and then Q over Q star, so the scale, to the power ns minus 1, plus perhaps if ns actually varies, then we write, excuse me, if ns varies with q, then we write another parameter alpha s over 2 log q over q star. And as you know, this ns minus 1 is much smaller than 1 in inflation, right? Experimentally, it's about what? It's about 0.025, right? So so then if this parameter is small and this is even smaller, so it doesn't matter, I can just consider this first term. Then I expand q to the ns minus 1 as approximately 1 minus ns minus 1 log q. But then delta s squared for holographic cosmology is something of the type 1 over 1 plus something times log q, which is also expanded when this something is small as 1 minus log this something log q. So these two parametrical forms are approximately equal anyway for the parameters that we're having. But the point is that the data is sufficiently complex that they can distinguish them. I mean, the CMBR fluctuations are now calculated to very, very precise numbers, and we have to fit all this acoustic curve with that. So so one can have a fit that is very complex, and yet the fit, so it could in principle distinguish them. That's that was the standard thing. You would think that the two should be distinguishable. And yet, in terms of the fit, I should have brought the two fits. Sorry, I forgot. I should have taken the two fits from out of some papers. But the point is, so the two fits don't fit perfectly in the same regions. Don't fit perfectly the data in the same regions. And yet, nevertheless, chi-squared is less than is within less than 1. So the difference between the two is 0.5, which is less than 1. Therefore, they are indistinguishable. Now, of course, the fit fixes parameters. And another thing I should have said is that one uses the same number of parameters as for the fit to inflation. Otherwise, you know, with sufficiently many parameters, you can fit anything. So one thing that one finds is that in the CMBR, if you look at angular L, which is less than 30, right? So L is like momentum is 1, roughly speaking. So these are very large angles. So small L's is very large angles on the sky. So one finds that this region, so on the fit, this region is non-perturbative. It goes away from the perturbative limit in which we calculated. So it has to be excluded. So in the fit, in the end, the region for L less than 30 was excluded because it did not correspond to the perturbative regime. So in order to put it back, one needs to do lattice calculation in order to be in the non-perturbative region that is needed. And this is work in progress. This is lattice work in process, and hopefully this should be done very soon. I mean, you know, I don't know really, but 2 or 3 years, maybe we should be able to distinguish which of the two fits is better. Is it holographic cosmology or inflation? Okay. Another quantity that is needed for the next idea that I'm going to present, the solution of the classic puzzles of Big Bang cosmology, is the global symmetry current correlator. So if I have some global symmetry current JIA, the 2-point function of the current, like the 2-point function of the energy momentum tensor, is written as a function of the effective coupling times a tensor structure. The tensor structure now it's much simpler. It's just this pi j delta pi k delta ik minus qi q k over q squared. And again, as before, we have this function of the dimensionless coupling has to be of the type constant times 1, and then g squared effective and g squared effective log g squared effective terms, and higher order terms come at 3 loops and higher. But I said global symmetry currents, and the action I took was phenomenological, so it means it had all possible terms, and so it didn't have any particular symmetry, global symmetry. Need some global symmetry, I have to restrict the phenomenological model. I have to invent some global symmetry. This thing will be related to monopole perturbations that we will describe shortly. So, okay, so now let me come to the puzzles of hot Big Bang cosmology. And first, let's see their solution in inflation. And
Before you go further, could I ask some questions?
Sure.
Could you go back to the slide 82? I had a couple themes there. So your partition function for the CFT has this spatial metric, but I didn't see, well, I guess this metric is a classical background spacetime.
No. So okay. So remember what the. So I see what you want to ask, but so it gets confusing because you have to think of the generalization of this Witten prescription for AdS. So what happens here in AdS? Phi 0 is a source for a current, right? An operator, but let's think of it as a current, right? And then on the other side, phi 0 is just a boundary source, right? So what happens here then? Hij is the thing that defines the wave function of the universe, which is a boundary source for the metric, but the spatial metric only, because you're looking in time at a fixed time. So Hij on the cosmology side is a boundary source, but the boundary source on the field theory side corresponds to a source for an operator, right? Oops, sorry. So Hij here is a source, right? It's just some numbers,
Okay.
right? It's not part of the theory. It's a source for what? What couples Hij? Tij, right? The energy momentum tensor. So this is just the source for the energy momentum tensor. And so when I vary with respect to it, I get functions, 2-point functions in particular for Tij, right?
Okay.
So
yeah, that's why it doesn't appear anymore in all the
that's right.
actions you're showing us. Okay.
So when I calculate things, I vary with respect to it and I put it to 0 at the end in order to calculate the 2-point functions. So that's how we arrived at this formula. I mean, it's a bit more complicated, but it's roughly this. So I vary with respect to Hij, and then I put it to 0, and I get this 2-point function. And then this is related to the power spectrum in the cosmology.
Okay. And also here you said, well, I think in the next slide or where you get the the ratio of the scalar perturbations for this generalized conformal something structure.
In this?
Yes, and in the next one, when you're comparing it to lambda CDM, yeah. So you said that, well, okay. So this expression in red, that's the one that you get in usual in inflation, right? And you say that you get something similar, and that for this well, nearly conformal field theory, and that. Well, it doesn't have a lot of freedom because that's kind of the only way that it can depend on the parameters, because it has this symmetry.
Yeah.
Okay, so it is like, well, I mean, that's a very big coincidence, right? Or was it?
No, it's not a coincidence, right? That's my point. So it's really you're saying why? So people will say, oh, inflation, you don't need to calculate anything because it's scale invariant. So that's why you see the scale invariant spectrum.
Yeah.
Fine. But there's the same explanation here. Generalized conformal structure is a symmetry which implies the same thing as for inflation. That's what I'm saying here. And I'm saying the corrections to it are small on both sides. So that's why, you know, the fits both are expected to work, at least if you have large errors. However, the interesting thing is that you have small error bars for CMBR, and nevertheless, the fit is indistinguishable. It could have been distinguishable. And in fact, as I said, with the new calculations of on the lattice, they will be distinguishable. So we will know which is better.
Okay, Thank you.
Sure. All right. So what are the big the puzzles of hot Big Bang? And we'll first see how they are resolved in inflation, and then what happens in holographic cosmology. So the first is the smoothness and the horizon problem. So this is the fact that the universe tiny perturbations, and moreover, there are correlations that are bigger than the observed horizon. So we see things that, like in one direction in the sky, is correlated with something in the opposite direction on the sky, even though the horizon, so the how much the light has been able to propagate, is smaller than the sky. So one concrete measure, so this is, I mean, GR is slightly confusing, so you might think that maybe this is just an error of calculation, but it's not. If you do things properly, what you must consider is the observed correlation size, which is 2 times the horizon radius, divided by the horizon distance at last scattering, which is when CMBR is formed, and you translate that to today. So the formula is this: it's 2RH at T0 today, divided by DH at the same. And this is approximately 2 times square root 1 plus Z last scattering, which is about 72. So we see correlations over 72 times the horizon that should have been true. And inflation solves that by saying that there's an expansion, which is either exponential or with a power greater than 1, which means that scales expand exponentially and they get outside the horizon. Scale gets outside the horizon during inflation. And then during usual radiation-dominated cosmology, usual cosmology with n less than 1, they get back inside the horizon. So that's really the explanation. And and this dH at T last scattering is proportional to this exponential, this blowout factor, this e to the number of e folds. Then there's the flatness problem, which is the following. If you calculate, use just FLRW cosmology, and you calculate the Friedmann equation, and you find that omega, which is rho over rho critical, minus 1, is k, which is plus minus 1 or 0, divided by a squared h squared. And that is proportional to t over a of t squared. So yeah, I used different number. Is the n, p is the same n as here. So so then this is proportional to t to the 2 times 1 minus p, or this n. So this means what? This means that the universe, so if p or n is less than 1, that means that omega minus 1 increases with time, right? So that means even if omega minus 1 was kind of small at some point, then it kept increasing. So now reversely, if we see that omega is really, really close to 1 nowadays, we go back in time, it should have been absurdly close to 1. Now, of course, you could say it is equal to 1, but that's a theoretical statement. It doesn't have anything to do with what we actually see experimentally. So experimentally, we just know omega is very close to 1. So so then why was it so fine-tuned in the past? And the explanation of inflation is rather simple, because it has either p greater than 1 or exponential, which means that omega minus 1 decreases during inflation. So omega 1 minus 1 decreases a lot during inflation and then starts to increase again during normal cosmology. Okay. Then we have the relic and monopole problems. Well, so what is the problems? The problem is we don't see neither monopoles nor relics. So direct searches for monopoles found that there are less than 10 to minus 30 monopoles per nucleon, which means that there's at the very least a 10 minus 30 monopoles per volume dilution of the monopoles. Why is that? Because if you consider the Kibble mechanism that generates, by definition, monopoles at a phase transition, the Kibble mechanism generates one monopole per horizon, one monopole per nucleon per horizon. And so we should have seen a lot of monopoles, right? Of the order of one monopole per nucleon. And that means that we need a dilution factor of at least log 10 to the 10, which is about 23 e-folds of inflation. So we need that many e-folds of inflation for a potential phase transition before inflation ends. And relics is even we even have another thing. We have if we had too many relics, they would overclose the universe, meaning the universe would be closed instead of being open as it is now. I mean, parabolic. So we would get 10. So we would need a 10 to at least 10 to minus 11 reduction in volume since the phase transition. So that's a smaller bound. Bigger bound is from monopoles. Then we have the entropy problem, which is the entropy today is huge. It's about 10 to the 88, the entropy in the observed horizon today. But even at Big Bang nucleosynthesis, which is the last time that we can say for sure what happened in cosmology, I mean, or the first time, well, you know what I mean. So so then it's still 10 to the 63. However, again, by the Kibble mechanism, at the phase transition, you generate one entropy unit per horizon. So that's kind of puzzling. How do you generate then so much entropy? Well, inflation is a large growth of entropy during reheating, and then exponential expansion also increases the entropy. So we generate a lot of entropy. There's the perturbation problem, which is that CMBR perturbations that we see in the sky are classical and were outside the horizon in the past, right? So why do we have these perturbations that are greater than horizon and classical? Well, in inflation, as I said, we generate quantum perturbations, and then they're exponentially blown up outside the horizon, and they just come back in now. So that's the solution. In inflation, we generate quantum perturbations, and they're just blown up outside the horizon. There's also the baryon asymmetry problem, but that is that inflation doesn't help too much with it. The baryon asymmetry is that the number of relative difference between baryon and anti-baryon is 10 to minus 9 in the universe. And in order to create baryon asymmetry, you need interactions out of equilibrium. And well, inflation helps in the sense that it's extremely fast expansion. And so it's much out of equilibrium, but doesn't tell you much more than that. Okay, so now let's see how we solve this in holographic cosmology. Well, so how about the first one, the smoothness and horizon problem. Well, you might first say, well, it's a non-geometrical phase. It doesn't matter. You can't explain, you can't use geometry. Yeah, but at the end, it should be geometrical. So it's not, you should still explain things. One thing you might think of is the holographic map is non-local. Even though the field theory itself is causal and local, the map to gravity is non-local. So it will generate some apparent non-locality. And that's certainly part of it. However, it turns out that the most important thing, the most important solution is that the field theory is actually finite in the infrared. And as we remember, we had said that inverse RG flow corresponds to evolution in time. And so in the infrared corresponds to small cosmological times. So Skenderis et al. Proved in, well, I forget, it was maybe last year, I think, an old conjecture about the finiteness of these three-dimensional quantum field theories that we're talking about. So the absence of infrared divergences, infrared finiteness, right? And that translates now to the fact that correlators are non-zero over large distances. So that means that there is no cosmological singularity. So cosmological singularity would correspond in the field theory to a singularity in correlators, but there's no singularity in correlators. So that means that there is an absence of cosmological singularity, which is much more than the solution to the smoothness and horizon problem that we wanted. And this gives also the fact that the light cones coming from different regions are correlated. But fine, so this is the actual solution, but let's suppose it's not. Let me just take, just so that we understand a little bit better what's going on. Let's suppose the theory would not be infrared finite. But let's define as the beginning the universe corresponding to g squared effective of the order of 1. Then this, the fact that there is a constraint on the number, remember, horizon problem generates a constraint of the number of e-folds for inflation. So this would correspond now to a constraint on the amount of RG flow in field theory. So let me be a little bit more precise about why this inverse RG flow or RG flow corresponds to inverse time evolution. If I consider a geodesic in anti-de Sitter joining two spatially separated points, then this would go through a minimum distance. It will go through AdS and then would have some minimum distance inside AdS that I call R0. But through the Vic rotation, this corresponds, so this R corresponds to E minus T over R. So that means that the scale L at which so the minimum distance in AdS is related to this separation L. So this separation L would be related to E minus T over R. And T over R means really in this case T times H. So inverting this, 1 over L is K, the scale corresponds to H e to the HT. So as you see, the evolution in K corresponds to evolution in cosmological time. All right. So RG flow corresponds to inverse time evolution, as we said. And we said that the horizon problem is solved because there's no cosmological singularity, and we have correlations of a large distances. But even if it weren't, we would be able to say that there was an amount of RG flow that is needed that corresponds to the amount of E-folds that was needed in inflation in order to fix the horizon problem. Now, this last form is also the solution of the flatness problem. Why is that? So how do I understand the flatness problem from the point of view of holographic cosmology? From the point of view of holographic cosmology, the flatness problem meant that there were some perturbations in gravity. Well, we said omega minus 1, but we can think of omega minus 1 as some sort of perturbation from omega equal 1. So the fact that we have this gravitational perturbation, it should decrease along time evolution. And as we said, time evolution is inverse RG flow. So the perturbations should decrease along the inverse RG flow. Inverse RG flow is from IR to UV. So that amounts to just seeing what happens to these functions, function f that appears in the two-point function of energy momentum tensors. So this function f had this generic form, but then we look at the coefficients now. So this leading coefficient f1, for the best fit to the CMBR and also for most of the theoretical parameter space is negative. So, and this dominates over everything else. So this f1 then, if I take it, so it's negative and I take it to be the leading behavior of f, then we get that, we get the following. If I would write this as q to some power, then expanding when the power is small, I'll get this 1 plus 2 delta log q. But g squared effective is proportional to 1 over q. So this would be 1 minus 2 delta log g squared effective. So comparing the two, we see that f1 negative corresponds to delta negative. And delta negative means what? Means that the energy momentum tensor is marginally relevant, meaning that the two-point function of the energy momentum tensor, two-point function of the energy momentum tensor decreases with q. So we get exactly the thing that we wanted. So when q increases from IR to UV, then the two-point function decreases. So perturbation decrease along this inverse RG flow. Now, we used CFT terminology when saying here things like marginally relevant, and yet we only have this generalized conformal structure. But the results are the same. The results are the same. So we have this coefficient f1 is negative, implies that this anomalous power delta is negative, which means dilution along this inverse RG flow. And then the amount needed to satisfy the observed flatness problem is still the same amount calculated in here. All right, the entropy problem. Well, the entropy problem is solved in inflation by reheating, we saw. Well, so now this holographic cosmology, we said it's kind of a strong coupling version of inflation. So it should be solved by a period that corresponds to reheating. But in field theory, it's kind of obvious. The dual field theory to the cosmology has what I would call gravitational modes, the things that give rise to gravity in the gravity dual, and the things that I would call standard model modes, which are the things that correspond to standard model particles in cosmology. And then what one has to the thing in the thing that corresponds to reheating is really a transfer of energy from one to the other, from these gravitational modes to these standard model modes. But in any case, the issue was, why do you see an increase, a very large increase in entropy? Well, remember that cosmological time evolution corresponds to inverse RG flow, right? So late times correspond to the UV and initial times correspond to the IR. But what happens in a field theory along this inverse RG flow? Number of degrees of freedom decreases along the RG flow, right? Because of Kadanoff blocking, right? When we do the RG flow, we consider an averaging of an over blocks, which amounts to a decrease of the number of degrees of freedom, which means that along the inverse RG flow, the degrees of freedom increase, right? So from IR to UV, the number of degrees of freedom increase, therefore the entropy increases. So then again, in order to get the right amount of increase, it will be again a constraint on the amount of RG flow. But so now this is perfectly natural and, you know, model independent really, because so in inflation we had reheating, and well, okay, that was also in some sense model independent, but the point is that now the solution is much more elegant. It's just this generic fact that we have the number of degrees of freedom decreasing along the RG flow, therefore increasing along the inverse RG flow. That corresponds to the entropy increasing. And as a bonus, this gives us the arrow of time, right? So well, we could say also that reheating gives the arrow of time in inflation, but now it's more than during reheating, right? This is the arrow of time at all times is defined by this quantum field theory notion of increase of the number of degrees of freedom along the inverse RG flow. Okay, the perturbation problem, it's also easier to understand in holographic cosmology, because the classical perturbations that one sees in the CMBR are dual to these quantum perturbations of the energy momentum tensor, which are just usual quantum field theory perturbations. And moreover, now there are no more assumptions. Why I say that? Because although, you know, in inflation, people say, well, there's no assumptions about perturbations, but there are actually two important assumptions. One is that we can use quantum field theory in Kerr space to calculate things, which, you know, you might say is reasonable, but it's still an assumption. And then further, one uses the Bunch-Davies vacuum initial conditions in order to, a specific initial condition in order to calculate the perturbations. That is not true in the holographic cosmology. In quantum field theory, the vacuum is the unique perturbative quantum field theory vacuum. There's no more choice of initial conditions or anything. And there's no extra assumption corresponding to quantum field theory in Kerr space. There's nothing like that now. For the baryon asymmetry problem, there's the same solution, but yeah, we could say also that there's no thermal equilibrium along the RG flow. Finally, the one problem that gives us some work to do is the relic and monoprobe problem. So so this is the problem of the problem that we have. We need to have a dilution of the number of monopoles because yeah, we find less than 1 monopole per 10 to the 30 nucleons and so on, and we should see of the order of 1. Now, how do we solve that in holographic cosmology? Well, first thing, you might also say the same thing, that, well, there's no geometry in gravity, so why do you care about monopoles in that? I mean, how can you explain something like monopole when there's no geometry? However, the point is the monopole is defined by topology, so you can define it abstractly, even in the absence of a geometry. And further, as we said also for the previous one, in the end, at the end of this phase, you still have to transition to usual geometrical phase. So then let's consider a monopole in the bulk, and let's think what that corresponds to on the boundary, on the 3-dimensional boundary. That would correspond to a vortex, right? So something that is topological and has magnetic charge in 2+1 dimensions is a vortex. Now, the true case that we would be interested in would be something like a 't Hooft monopole, which is a monopole in the non-abelian theory that has no singularity at the core. And that would correspond on the boundary to a true vortex, which is also in the same spirit, is non-abelian and has no singularity at the core. But that is extremely hard to consider. So the only thing we can do is to consider an approximate case where instead of the 't Hooft monopole in the bulk, I consider a Dirac monopole, which is, this point-like abelian monopole with a singularity and a Dirac string. And correspondingly on the boundary, there would be some corresponding singular object that I decided to call a Dirac vortex. So this is the only thing that we can work with. So we have to dilute these Dirac monopoles in the bulk, and therefore we would need some sort of dilution mechanism for the Dirac vortices. So what does that correspond to? Well, first of all, there's a constraint. The constraint would be described in terms of the monopole currents in the bulk. So like for the perturbations problem, we would say that we would dilute perturbations of the monopole current, which means the 2-point function of monopole current should be diluted. So during the cosmological time, that means inverse RG flow, we need to be diluted, which turns out that this means that the the anomalous dimension delta of these monopole currents should be negative, as we saw in this previous case, right? So for the flatness problem, we saw the same thing. We needed delta to be negative to have dilution. Yeah, for relics which couple to Tij, we need dilution of Tij, which already saw, and so it's also a less stringent constraint, so we'll not consider this. We'll just consider monopoles. Then a gauge field in the bulk corresponds to a global current in the QFT. And also, you note that we don't know at this point how to deal with magnetic currents, so we have to consider electric currents. So Noether currents. But since I emphasize that the quantum field theory is phenomenological, so I don't know how to define a symmetry current in a phenomenological theory, because it doesn't have a symmetry if it's arbitrary. So that means that I need to consider a toy model. I need to focus on a model with some symmetry. So we consider a toy model, but a posteriori we found in this paper that the calculation is valid for all relevant models with a global symmetry. So let's consider a model with an SO3 global symmetry that allows vortex solutions. And we've considered this model with the gauge field and 6 complex scalars with one index, which is 1 and 2, and one is SO3 index. And then the potential is this one. Then we can write down the Noether currents. And then we do exactly the same kind of two-loop calculation for the two-point function as was done for the energy momentum tensor. So now we do it for the global symmetry currents. And well, this thing has divergences, but they are removed since the momentum dependence that we're after, it's only in the finite piece. And we find some result like that. And again, we have to match this with the expectation. What do we believe it should look like? Well, from generalized conformal structure, as I said, this should have a given tensor structure, this pi mu, which is delta mu minus q mu over q squared, and then a function of g squared effective, and moreover, the leading term is g squared effective log g squared effective. But g squared effective is proportional to 1/p, so then when I replace this log with log p, I get, instead of plus here, I get a minus. And then if this would be generically as before proportional to p to 1 plus 2 times the anomalous dimension delta, then we would get plus 2 delta log p. And so this 2 times anomalous dimension is minus coefficient times g squared effective. And we obtain that this delta, the anomalous dimension, is positive, which means the Noether current is irrelevant. It grows in the UV, not in the IR. But now we remember that we don't need the Noether current, we need the vortex current, the magnetically dual current. So then we find, well, okay, so there's a transformation in an abelian model. One can write a transformation between the Noether current and the vortex current. But there's a precise relation that was calculated by Witten in the abelian case and Herzog, Kovtun, Sagittarius, and so on in the non-abelian case. They said that if we have a conformal field theory, the two-point function goes over from the electric two-point function. So the electric two-point function is written in terms of a coefficient T and the coefficient parity breaking coefficient W. And then the magnetic current two-point function is written in terms of this new structure, T over T squared plus W squared and W over T squared plus W squared. If I don't have this parity breaking term W, then the going from electric two-point function to magnetic two-point function amounts basically just to inverting this coefficient T. Inverting it, so this was in the abelian case, and in the non-abelian case, one basically just replaces this scalar coefficient with a group valued coefficient KAB, and then going from electric to vortex corresponds to just matrix inversion of this coefficient. Okay, so now we can consider our calculation, and so we obtain for this non-abelian Noether current two-point function. We saw that we obtained. Oh, actually, I forgot to write. There's actually delta AB in here. That was the. Yeah. Oh, sorry. It's in here. Yeah. So so as far as the symmetry, as far as the group indices is concerned, it's like abelian. It's delta AB. So so the matrix inverse is just delta AB times the regular inverse of the coefficient. Oops, sorry. And so basically I have to just invert this thing, which means invert the delta, right? So that means going from 1 plus 2 delta log P to 1 minus 2 delta log P. Oh, delta tilde, right? Sorry. So delta tilde is minus delta. So that means that and I should note that this is the effect of an S duality, which is nothing but the usual Maxwell duality exchanging electric and magnetic in the bulk. So the effect of this electric magnetic duality exchanging Noether currents for vortex currents is just changing the sign of the anomalous dimension. And since we obtained that the anomalous dimension was positive, meaning the Noether current was irrelevant, that means that the magnetic current has negative anomalous dimension, which means it is relevant as we wanted. Relevant means that it grows from UV to IR. So along the inverse RG flow from IR to UV, it decreases. Therefore, the monopole perturbations decrease in this cosmological time as we wanted. The only extra thing that one needs to check is that the theory actually has a vortex solution. So we've considered some toy model, written here with this potential. So we have to check that this has this, well, Dirac vortex, not normal vortex, but Dirac vortex solution. And indeed it has. I've checked an ansatz that keeps the potential 0, and on this ansatz, we obtain a Dirac vortex solution, which means a point-like vortex with a singularity. And so because we have this vortex, we do have a vortex number and an actual vortex current, because otherwise it would be meaningless to say that we did a duality transformation between Noether current and vortex current if we didn't have a vortex. But we do have a vortex, so things are okay. And finally, that means that we've solved the monopole problem as well. We have found that monopole perturbations decrease along this inverse RG flow, which is cosmological time. So the monopole solution was also solved. That means that all problems with the original hot Big Bang cosmology are also solved, just like inflation solves them. And we saw that the CMBR fit was as well as for inflation for the holographic cosmology gene. So what does it mean? What does it's missing then to be at the same level as inflation? Well, one thing that is missing is really a well-defined reheating model, or rather for the equivalent of reheating in holographic cosmology. So the reheating, it means the transition from this phase, in this case a non-geometrical phase, to the usual radiation-dominated cosmology. And inflation was the transition between inflation and radiation-dominated cosmology. But so we did, there is a sketch of one available in a paper I wrote in 2020, but a more precise one is needed. And so the problem with that is that one needs to reverse the direction of the flow of the coupling, of the RG flow, if you want. Because during this non-geometrical phase, the coupling is the Yang-Niels coupling is getting weaker. So it's very strong at the beginning and very weak at the end, which means reversely in gravity, it's the opposite. Gravity is becoming stronger during this cosmological time. So, but of course, gravity must eventually start to becoming weaker in radiation domination. Gravity is becoming weaker, right? The universe is expanding and gravity is becoming weaker. So that means that we must reverse this flow. And I sketched how one can do things in this paper, but there are many things that are not complete there. And finally, I told you that there is the lattice field theory calculation that is ongoing for some time now, but these things take time, by the group, lattice group that contains Kostas Skenderis. And this will eventually do a test for matching the CMBR at low L, low angular momentum L, but L less than 30, which corresponds to the large distances in the sky, large angles in the sky. And one should see whether it's actually inflation or holographic cosmology which is better, because in this region the two are really different and none of them fits perfectly with the data at this point. So it would be interesting to see whether the fit becomes better or worse when that is done. So yeah, we'll wait for the solution of these two things, but I hope that holographic cosmology will actually be a new contender parallel to inflation. So that's the end of my talk and my series. Thanks a lot.
Thank you so much, Horatiu, for these lectures, brilliant lectures. Any questions? This is your last chance to talk to Professor Nastase. Okay, so
I have another question.
go ahead. Yes.
Okay.
So I don't know if I got lost at some point or what happened, because I thought you were you started with this model that was constructed by Maldacena, where you do these big rotations and then you can work in the theta, right? But then when you were arguing, especially in your first point in this list of problems that you are solving, you at some point argue with that in AdS there's a minimum distance between well, of minimum length of a geodesic joining two points. And so then I got confused about are you working in the theta or on in anti-de theta?
No, that was okay. That was just in order to motivate I mean to well, not motivate, to give a stronger explanation on why inverse RG flow corresponds to time evolution in cosmology. So the point was that in anti-de Sitter, I can make that that extremely precise by the argument I just gave. Now, after you do the Vig rotation to the Sitter and further you go away from the Sitter to some other gravity dual, then it becomes less clear. But this is not, you know, this is not about the actual functional form. It's only about the fact that the arrow points in that direction, right? That's all I wanted to argue for. So.
Okay, we have a question. Sade, would you like to ask? Okay.
Yes. Can you hear me?
Yeah.
First of all, Professor, I would like to thank for your interesting lecture. I need to review again more and more. My question is about the sense of information in a case of holography. Is it true that the holography information can be put on a surface of a space in a lower dimensional? For example, in an interior surface of black holes. Is it true or not? Thank you.
Well, so yeah, in terms of the actual, perhaps I'm not the best person to reply in a precise way on how that is done, but just as a generic issue. So one believes nowadays that all gravity is holographic. So there's then two ways in which that can happen, right? So that means that you can take the physics in the bulk and project it onto a surface. But which surface? Now here the things become a little bit dependent on your background, right? So if you have anti-de Sitter, then it's clear. On anti-de Sitter, you can always project the bulk physics onto the boundary. So anti-de Sitter is thought of as a cylinder, and you can basically project on the surface of the cylinder everything. Now, if you have a black hole in anti-de Sitter, then you have a choice actually. So that's one of the things that is interesting, is that you can project also to the surface of the black hole. This goes under the name of membrane paradigm. So that is a possibility. Now, if you have more complicated spaces and you have black holes in them, then the issue is more complicated, and I don't think, yeah, I don't think there's well, general story. I might be wrong. So one can project onto some light-like surface. There's a proposal to project holographically onto a light-like surface into a generic, let's say, asymptotically Minkowski even space. But to the surface of a black hole, you can certainly project the physics nearby, but I'm not sure how far away does that extend, right? So if you have a physics enclosed in a certain surface around the black hole, you can certainly project that onto the surface of the black hole, making it locally holographic. But yeah, for asymptotically Minkowski, I don't know if that is possible in any meaningful way.
Thank you. It means, Professor, it means that the information is permanent or temporarily. For example,
no, it's not. It's not that. No, it's not. So it's how should I say? So you're thinking of something like a real hologram, right? So when you take a real hologram, you imprint on the hologram, you imprint the image of a three-dimensional object, but it's the image, right? So it's not the object that's imprinted, right? So it's so if you that's what I mean. When you think of this as a physical process of imprinting, you're not transferring the object onto the surface, you're just making an image for it. But once the image is made, the two are equivalent. The image, the holographic image of three-dimensional object, and the hologram, the two-dimensional thing. That's the analogy that one has for holography in gravity, right? So the physics is completely equivalent. It's not, so you can extract any information either from the boundary or from the bulk. It's equivalent. It's not deleted from somewhere and goes somewhere else, right?
Thank you very much. My final question: in higher dimensions, also this information, it's a constant or will be changed. For example, the image that you said about about this information. I want to know that just in a lower dimension, this information will register, for example, on a surface as a shadow or anything, or in a higher dimension will be changed, for example, the formation of information.
No, this is valid in any dimension, right? It doesn't matter. So in particular, as I was saying, the original AdS CFT is for AdS 5 cross S5, so a 5-dimensional space once you reduce on S5, projected onto 4 dimensions, right? And then in higher dimensions, you have, for instance, the AdS 7 projected into 6 dimensions, right? So that's really really the picture. So when we're talking about surfaces, we're always talking about generically about hypersurfaces, right?
Thank you very much, and I really appreciate it.
Sure.
So it's just 1 dimension less than the bulk, right? That's what we mean.
Yeah.
Okay. So any other questions?
Yeah, so in this model that you showed us, there is no supersymmetry hidden.
No, right? So that's it's a phenomenological model, so it's not. You can restrict to a supersymmetric model, and I have tried to do that, but then it becomes very difficult to fit the data, CMBR data with it. So it seems to be, so at least naive supersymmetric models, so like n equal 4 spamials, for instance, do not fit the CMBR data. So the
Okay.
CMBR data has more scalars than fermions.
Okay, so this is really like a 4-dimensional universe and a 3-dimensional boundary theory.
Yeah, so no, I said
compact
for
directions.
reduced. I meant reduced to 3 dimensions.
Okay, okay. And well, maybe in the spirit of this, the name of the lecture's basics of quantum gravity. I mean, this is so. I am asking your personal opinion on it. How much do you think we can realistically learn of quantum gravity in our universe from holography or AdS CFT or even string theory?
Well, so as I said, perturbative quantum gravity, I think, well, people might disagree, but I don't think there's any other way in which to obtain a finite perturbative quantum gravity other than string theory. Now, the interesting issue is non-perturbative, how do you get, how do you learn about a non-perturbative quantum gravity? Because we don't have a non-perturbative definition of string theory. Or, well, any other completely satisfactory theory of quantum gravity that is valid in both perturbative and non-perturbative regimes. So, so for that, the question is, well, so we have this tool, AdS CFT, right? So we think we know quantum field theory. And then assuming, as I've said, there are a bunch of tests that say that AdS CFT should be valid at all couplings, therefore also for the case that corresponds to non-perturbative quantum gravity. That's why we applied it here for holographic cosmology. But the interesting thing would be to learn what non-perturbative quantum gravity means, to define it, right? Because the way we do so now is just, calculating its effects without knowing what it is, right? So in particular, I've calculated 2-point functions of perturbations Hij without knowing how those are defined in a non-perturbative quantum gravity. I just assume this map and I calculated in field theory, right? So for that, it's harder to say. I mean, hopefully, I mean, I tried a few things, but it's very, it's very difficult to find. The AdS CFT offers you some ideas, but it's unclear how to, at this point, how to make it better. We can hope that somebody will come and will define this holographic map non-perturbatively. So then we'll know. Yeah. Otherwise, we can still, in principle, if all you're interested in are formulas, you might not even need to define it, right?
Yeah,
right?
well, depends on what the question that you want to answer, right?
That's what I mean. That's what I mean. So yeah. Like, we've solved the complete problem here. How do you define perturbations, quantum perturbations, 2-point functions of perturbations in non-perturbative quantum gravity? We've calculated it, right?
Mm-hmm.
So what else do you want to know, right? So this is for cosmology. Now you can ask, well, other relevant questions would be, what happens near a black hole, perhaps. I don't know. So all of these questions are studied by string theorists using AdS CFT. So yeah, if that's all you want, then we made great progress. But to define really, no,
Yeah.
you know, just put it on a computer and you're done. Yeah, we're not there.
Yeah. So
Thank you.
Thank you for your questions, Alicia. Regarding these inflationary models, basically we are dealing with de Sitter spacetime without supersymmetry because they don't go together, right? So I'm reminded of a joke by Eva Silverstein. That's why people say string theories are anti-de Sitter. So
Okay.
now. Horatiu, today you taught us lots of things about the holographic cosmology. My question is, how different is it from DS CFT correspondence, de Sitter CFT correspondence? Are they two different things?
Well, no, that's where it was started from, but
Right. Yes.
What I'm saying is the Sitter CFT means different things to different people. So various people have their own impressions. What I'm saying is the application to cosmology was written in this
Is the holographic
really huge, really important paper of Maldacena from 2003. So, you know, this is a paper that cosmologists use a lot.
Okay.
Right?
Okay.
But he did it just for perturbative de Sitter, so in perturbative inflation. And the issue is that, so in fact, one is still not convinced that this works for the cases we applied it to. Well, but so it is an extrapolation, but I think it's well defined. So in particular, as I was saying, the holographic calculation was done in two ways. One was using his map, which is just taken from de Sitter, and then the original one that McFadden and Skanderis actually did was using a Hamiltonian formulation for AdS CFT developed by Skanderis and Papadimitriou, and so they match, and so I think yeah, to my mind, this is you know, very well defined, the extension from de Sitter CFT to this case, but unfortunately, not everybody is convinced. So,
but it's impressive that you take problem by problem, saying, okay, what does inflation do? What holographic cosmology do? That's really impressive. Regarding that, I have a question. What about the prediction of B modes in holographic cosmology? For example, ekpyrotic universe, they say no, it doesn't exist. Whereas inflation, yes, some models have more than the other.
It exists. They've been calculated. Yes. I mean, so the other point is, as I was saying, the spectrum has been calculated, but I haven't shown because, you know, it's not. This is in the future, so I just want to show the things that we know now. But so the other thing is, as I said, you have to think of holographic cosmology as an extension of inflation into the strongly coupled regime. That's really the way to think about it.
Okay.
And so that's unlike ekpyrotic or cyclic or so, which are different paradigms, right? This is an extension of the paradigm into the strongly coupled regime, which means that at some level it was expected to work at the, so you would just because it's just that you are now in different parametrical regime that you expect maybe you could find deviations, but yeah, the deviations are actually not big. So anything that you solve with inflation, you can solve with holographic cosmology.
Okay. See, the last point on the slide you have is about the low multiple fitting, right? So
Yes.
People say this is because of the cosmic variance. So we will never be able to fit it perfectly because we have only one data set.
No, that's true. That's true. But you know, so I didn't I didn't show you here the graphs. I should have perhaps the matching. But so the matching is at small l is at the moment is really different between inflation and holographic cosmology. And the point is not that you're matching just there. The point is that you take a matching that works everywhere and you use it to match also at low L.
Okay.
So this chi-squared of 800 and something is you know, it's over the whole region of L's, which will be modified. So yeah, the results will be different, really. I mean, it will be you know, a huge surprise if the magic stays the same.
Okay.
There's no reason for it. Yeah.
I was very impressed by seeing those chi-square numbers. Any numbers is good. We are getting more realistic, and that's fantastic. Any other questions?
Just like this paper by Maldacena that you have been mentioning is the one non-Gaussian features of primordial partitions. Okay, good.
Yeah. And there is another paper, 2017. I don't know, recently in Physical Review Letters, by lots of authors. I think Horatiu mentioned that they also talk about the Planck data and holographic cosmology, right? I guess these chi-square values come from that paper.
Yeah. So I've this paper, this one.
That's correct. Yeah, 2017. Exactly. Yes, that's correct. Yes. Okay. So if there are no more questions, we can all thank Horatiu, Nastase for such nice set of lectures. Thank you so much for everything. And I strongly advise everybody to go check out his books, including the ones related to what we have. Okay. So, okay then. Thank you so much.
Thank you.
Thanks. Bye.
Thank you.